Now, with energy, the key thing to understand is what is energy in simple terms. So there's this nice summary that I want us to go into. It is going to save us a lot of time. It is also going to emphasize key issues that one now needs to know. But it basically says to me, first things first is for me now to fully explain what is energy. So we define energy as the ability to do work, and is a scalar quantity. So it being a scalar quantity, it basically says it must have now magnitude only. So there will never be a point where I am expected to explain or to give direction for energy, because energy is just now a scalar quantity. So remember, a scalar quantity is a physical quantity with now magnitude only. So with that being said, we now have two different types of energies. The first one is what we call gravitational potential energy. The second one is what we call kinetic energy. But what is the difference now between the two? The difference between the two is that now this gravitational potential energy is the energy an object possesses due to its position to a reference point. So we are looking at an energy that an object will possess or have due to its position. But now we will always have a reference point, a point that we can use to say at this specific height, this is now what the energy that or gravitational potential energy that an object will possess. So a reference point is basically, in our case, will always be it having a specific or a certain height. So we understand by saying is the energy an object possesses due to its position relative to a reference point. So there are two key things there. One, object possesses due to its position, but that position, there has to be a certain specific reference point. We further move on to say an amount of energy transferred when an object changes position relative to Earth's surface, it is given now by this equation there. So the equation for us to calculate EP, which is now potential energy, it is just now M is equals to EP is equals to mgh. But there are key things that we also need now to understand when we look into this. Our mass must be in kg and our height must be in meters. And then G now becomes a constant, and that we will get now from our formula sheet. So it will be just G is equals to 9.8 meters per second squared. So if you check an example here, it says now determine the gravitational potential energy of a 500 gram ball when it is placed on a table with a height now of 3 meters. But what is key here? First thing is to realize that our mass is given as 500 grams. So we agreed that our mass now must be in kg. So how do I get it into kg? I must divide by 1000. then it will give me 0.5 kg. Then I will be able now to substitute the correct values thereof. So because of this, it allows us to say we are using the correct SI units for everything that we are going to do. So the only thing that we need now to emphasize is the final answer being correct together with the correct now SI unit. What is the SI unit for energy? The SI unit for energy is now joules, and then we only write a capital letter J for us to give the correct SI unit for energy that we now calculate. But now, this is basically it with gravitational potential energy. But we have another energy that we also need to focus and look into. What is that energy? That energy is called the kinetic energy. So kinetic energy is the energy an object has as a result of object's motion. So what is this now saying to us? This is basically saying we need to have an object now that is moving. So for me to talk of kinetic energy, the object should be moving. So the object moving in this instance the object will possess the type of energy which we call kinetic energy. So kinetic energy is the energy an object has as a result of its motion. So it basically says the object should be moving. And for us to calculate that, the correct equation will be EK is equals to half mv squared, where now the m is for the mass and must be in kg, and v now must be in meters per second. So some questions that we are going to come across, we will be given our velocity not in meters per second, but we will be expected now to use this equation. So for us to use this specific equation, we need to have our velocity in meters per second. So with that, it says once I have a different SI unit for velocity, then I must now convert that to meters per second. So once we get into that question is then that will emphasize more on how to go about ensuring that we have the correct SI unit. Then let's look at this example here. They say determine the kinetic energy of a 500 ball when it travels with a velocity of 3 meters per second. So key thing is to highlight the data given to us. I have our mass there, which is 500. So I must convert this mass to kg, which will be 0.5 kg by dividing now with 1,000. I have my velocity, which is 3 meters per second. Then I just write my formula, half multiplied by 0.5. And remember, the v has a squared. Then I finally get my correct answer, which is 2.25 joules. So this is the two energies that we need now to focus on. We need to know the definitions. We also need now to apply the correct formulas when we are given certain calculations to perform. But now everything here, what is important is once we understand how each will influence in terms of the SI units, then we are in a right way of saying if I am working with EP is equals to mgh, then my height must be in meters and my mass must be in kg. If I am working now with EK is equals to half mv squared, my mass must be in kg and my velocity must be in meters per second. So this is now key in ensuring that we are working with the correct SI unit. Any questions, Ratanang, so far?
No, I don't have any questions.
Okay, thank you very much. If there are no questions, then it basically says we can now move to mechanical energy. So mechanical energy is defined as the sum of gravitational potential energy and kinetic energy at a point. Now, with this, it basically says it's just now the sum of EP and EK. But what is key with me? Remember, EP is now what? An energy an object possesses due to its position. So it basically says, I am going to check in terms of the height given exactly where is the position that we are looking into. So because of that, one can be able to say, let's look into this example. And when we look into this example, we say a ball of mass 500 gram is thrown horizontally through the air. The ball travels at a velocity of 1.8 meters per second and is 2.5 from the ground. Determine the mechanical energy of the ball. So they always now start with the formula, which will be EM is equals to EP plus now EK. But what is the mass? 0.5. What is G? 9.8 because it's always given, and the height is 2.5. Do I have anything that is now kinetic energy related? Yes, I have now 1 over 2. The mass is given 0.5, and I have now V, which is 1.8 meters per second, and the sum of the two will now become my mechanical energy. So just remember, mechanical energy is just now or the sum of the gravitational potential energy and the kinetic energy at a specific point. So that is now a mechanical energy. Let's further move on to principle of conservation of mechanical energy. Principle of conservation of mechanical energy. So what is key here with principle of mechanical energy? One is you must be able to state and you must also be able now to apply. So it is one of the principles that the examiners love a lot because they realize that there are a lot of challenges when it comes to this. So you must be in a position to apply, and you must be also in a position to state it, because now once you state it, you'll be in a position of getting maximum marks. So this is what it says. In this slide, they say, in the absence of air resistance or external forces, the mechanical energy of the system remains constant. So I'm going to write it this way because that is how now we want it to be in an exam. So in an exam, this is what you say. You say now the total mechanical energy, let me write here, the total mechanical energy in an isolated system is conserved. This is now what we say and what we want to be looking for when we say now state the conservation of mechanical energy. So the conservation of mechanical energy is basically says the total mechanical energy in an isolated system is conserved. But now one will ask, let me add a page quickly. Let's talk now at 3, conservation of mechanical energy. Now, with conservation of mechanical energy, it says the total mechanical energy, the total mechanical energy in an isolated system is conserved. So there are keywords that one will be looking for. Total mechanical energy, isolated system, conserved. So let's break it down in simple terms. At 3.1, we have now the isolated system. What is this isolated system? So the isolated system is a system in which the external force or the net resultant force is equals to 0, or a system in which there are no external forces. So with that being said, it basically says we are now in a position of understanding exactly, for one to say we have conservation of mechanical energy, then it means we should not have any form of a friction. So let's write it down for you to be able to remember. Isolated system, a system in which the net external force is 0. Some guides will say a system in which there are no external forces. But now remember, we always have external forces. The issue is just how much of that we have. So it's a system in which the net external force is 0. So key thing that you need to be looking for. Key thing now at number 3.2, which is now a hint. Now it says look for words like ignore, friction, absence of friction, no air resistance. So now these ones are keywords to look for before applying the principle. So what does this say? It says to me we can only apply the conservation of mechanical energy only if I am told that I must ignore effects of friction. I must now look for the word like absence of friction, something like no air resistance. The reason for that is mechanical energy is only conserved. We'll write it down. Is only conserved when there is no friction. So once there is friction, then we can easily say the mechanical energy is not conserved. So key thing that we are looking for is for us to say conservation of mechanical energy, or there is conservation of mechanical energy. Definitely we must be now looking for no friction, because now once we have friction, it basically says the mechanical energy is not conserved. So that is the key thing that we need to look for. Once they tell us that the friction can be ignored, there is no friction, then automatically to mind should come conservation of mechanical energy. But this conservation of mechanical energy, it's basically E of at the top is equals to E at the bottom. Let's look into it. We said basically mechanical energy is just EP plus now EK. So what does conservation mean? Conservation means before should be equals to after. So we are going to take the same equation that we have of saying EP plus now EK before should be equals to EP plus now EK after. At times people use top and bottom, but it does not really matter, because what we are interested is what happened now before and what is it that is happening immediately thereafter. So this is one key equation that all of us, or we will be expected now to apply. So whenever you start working on a problem or a question given to you, you need to state it as it is, because for you to say EP plus EK before is equals to EP plus EK after, already you will be getting that 1 mark that we need for the formula. So basically, what does this say? It says now, I'm also going to have my reference point as per where and the position of the object. So because of the position of the object, then I can easily now focus on having what? On having exactly, or knowing where is my object in terms of the EP, also in terms of the kinetic energy thereof. So there will always be one variable that we are calculating. So you need now to be in a position of fully trying to explain this specific equation. So any questions up to this far relating to conservation of mechanical energy?
No, I don't have any questions.
Okay, thank you very much. Let's look into the examples then. Example number 1 says an object that is now moving vertical. A 2 kg ball is dropped from a rest position. Now, here comes other nice trick words that we need to look for. Rest. So once they say it is at rest, it basically says V initial is equals to 0 meters per second. So there will always be those words at rest, stationary, or it is dropped for us to start looking for. The reason for that is they are not going to give us everything as easy as we think we will, but we will be in a position of ensuring that we fully understand the science behind the statement the statement given. So it basically says now a 2 kg ball is dropped from rest. Determine the maximum velocity of the ball at B just before the impact. So it's always nice to have your data. So let's write exactly what is happening at the top. Now at the top, I have my V, which is equals to 0 meters per second. And then I have my height here, which is now 4 meters. But at B is what I am looking to get. But now because the ball now is at the ground, it basically says the height thereof must be 0. So if the height is 0, then we know this information should be correct, and it's just now an issue of applying that. So let's look at how we will allocate marks for this. We remember we always start by writing the formula as it is, because it is a principle. We must start now by saying EP plus EK at A is equals to now EP plus EK at B. So hence I say the formula is not now cast in stone. You can modify in order for you to be in a position of fully understanding where you are in the question. So it will just be now the mass that is in kg 2, and we have now 9.8 multiplied by 4. And then we have our initial velocity being 0 at A. And now we can easily substitute everything that is given and then end up with our final answer, which is 8.85 meters per second. So now for example number 2, remember we always need now to have a reference point. So our reference point in this instance is A to B, but now this object, it's moving now on an inclined plane. So once it is moving on an inclined plane, it basically says it is moving upwards in this direction with 3 meters per second at A, because it is at the bottom, it is the ground. So H should be 0. And then we are interested in getting now the height at B. So this is a different set of question, but still we must now start applying the conservation of mechanical energy. Then everything will be fine and easy. Then your final answer should be 0.46. Then let's look into example 3. Example 3, it's now the pendulum. It's now the pendulum. A 2 kg pendulum swings from A at 5 meters per second to B on the ground where the velocity is 8 meters per second. Determine the height now at A. Now look into this. With this, we also start with our conservation of mechanical energy. So that is the pattern. You must always start with the conservation of mechanical energy. But how and when will one know that I am going to apply conservation of mechanical energy? It's very easy. Just read the statement. Once you are told somewhere that ignore the effects of friction, absence of friction, no air resistance, then we'll be knowing that mechanical energy is conserved. Now, let's further move on to a roller coaster. The 2 kg ball rolls in a toy roller coaster from A at 20 meters above the ground to B, where its height is 8 meters and the velocity is 14 point or 14 meters per second. Calculate its starting velocity at A. Remember, we always need now to have 2 points in this instance. We have our point there at A. We have now our point now at B. So the data should now be the one guiding us as to exactly where we are in this question. So start with the formula. Just remember independent formulas in terms of mgh plus half mv squared. Then this is now at A, and this is at A also. That is now at B, and this is at B. Then we'll be in a position of getting your final answer as 10,84 meters per second. Any questions?
No, I don't have any questions.
Okay. Is it clear though in terms of how to apply conservation of mechanical energy? Because that is where now most people lose it. But once you are told that ignore effects of friction, the chances are 100% you are going to apply conservation of mechanical energy.
No, I get it.
Okay. Thank you very much. Let's move on. Then with that being said, it basically says this is the overview summary of this particular topic. So what is it that is left? It's just us now applying everything that is given to us, or also exposing ourselves to more of an exam type of a question. But before we do that, I want us to do this example just to check where we are in terms of understanding each concept. So I will give you some time. This you should be now in a position of doing it in the next 3 minutes. So I will give you that, and then quickly send me your answer then. Do you have an answer for me?
Yes. My
Okay.
answer is 235.2 joules.
Okay. So we start basically by saying, let's look for the data. A father lifts a child with mass 20 kg, 1,2 above the ground. Then we must calculate the potential gravitational energy. So this one will be an easy one to do. Just to say EP is equals to mgh. Then the mass is 20 multiplied by 9.8, which is a constant, and we are told the height is 1,2. So if you take your calculator, this should be, what's the answer? So this should be
my answer is 235.2.
235,2 joules. 235,2 joules. And then that is us now getting our nice 3 marks. Let's quickly do this one. Let's skip that one and come into this. Let's quickly do this one. Let's quickly do this one. It's 14 marks. So I'm going to give you 13 minutes to do it. That's if we have the 13 minutes, but try to be quick. Okay, now that you are done, let's quickly try to check if you got this correct. So at 5.11, they want us to convert 14 meters per second to kilometers per hour. But in most cases, it's always the other way around, like from kilometers per hour to, they wanted us to convert 14 meters per second to kilometers per hour. So remember we spoke when we were doing waves to say for us to move from seconds to to hours, we must multiply by 3000. But now for us to move from meters to kilometers, we must divide now by 1000. So that is the reason why we have this 3600 divided by 1000. But there's a trick that most of people use. They basically say 14 multiplied by 3,6. So it basically says when moving from kilometers, meters per second, you multiply by 3,6. And when you move now from, you divide by 3,6. Okay, let me write that 3,6, correct. You divide now by 3,6. So this will give us now 50,4 kilometers per hour. So with this, it's just an easy way to say, where is my starting point? Am I starting from meters per second to kilometers per hour? Am I starting from kilometers per hour to meters per second? If that's the case, then I must just know when to multiply by 3,6 and when to divide by 3,6. They will accept it, but at times they are looking for 3000 divided by 1000. Then at 5.2, it says now define the term kinetic energy. So kinetic energy, we did say it's an energy possessed by an object as a result of its motion. So remember, this one is a definition. So if it's a definition, it should be now 2 marks. And you should be having the keywords that we are looking for. Energy that an object possesses as a result of its motion. Then at 5.3, they say now calculate the gravitational potential energy of a cell phone at a height of 5 meters above the ground. So when we check the information given, we are told that the mass of the cell phone is 0.01 kg. We are also told that it is 10 meters above, but the examiner is interested in us finding the energy at 5 meters above the ground. So it's easy. We start by writing down the formula, which will be now EP is equals to mgh. Then I have my mass, which is 0.01, multiply now by 9.8, multiply by 5. So remember, our height must always be in meters. So hence we have to multiply by 5. Then we say now the final answer should be something like 0.4949 joules. So by doing this, everything now becomes easy. It's 1 for the formula, 1 for the whole substitution being correct, and then the final one, it's now for the final answer. The final one, it's for the final answer. So that is now an easy 3 marks that one can be able to get. So with this topic, it's just an issue of exposing ourselves more to the type of exam questions. So let's move on to say now at 5.4, it says calculate the velocity of the cell phone at a height of 5 meters above the ground. So what is it that this examiner is trying to assess? They've given us the velocity, but now that velocity, it is now at the bottom. So this is what the examiner is saying. The examiner is interested to know what is now V at 5. So this is what the examiner is saying. So what do we have? what we have is, we know that it was dropped, so V initial will be 0 at the top. We also know that our height before was now 10 meters, so this is now H before, and we have everything thereof, so we are interested in what is the V here. So what is it that we can use, because we have now two reference points. We have the top of the floor and we have this part here which is now at 5 meters. So remember, I said the examiner will always have a way of telling us or giving us the reference point to focus on. So let's write now an equation that we can use. Once we have two reference points, top of the floor and now at 5 meters, it basically says I have 2 points of which I need to consider. Can I apply conservation of mechanical energy? I have to be looking for something else. What something else? The statement says now ignore the effects of air resistance. So for that statement that says ignore the effects of air resistance, it gives me a hint. It tells me more to say definitely this will be now a way of me applying a conservation of mechanical energy. So the fact that I am told that I must ignore, then definitely I must apply that. Let's see how can one best apply the conservation of mechanical energy. So we are at 5.4. So at 5.4, we say EK or EP plus EK at the top now is just equals to EP plus now EK at the bottom. But now remember, our bottom now is at 5 meters. Then it's easy for one to say I have the mass, which is 0.01. I have the G, which is 9.8. I also have now the height. It was 10 at the top, plus EK, it was dropped. It will be half, multiply by the mass 0.01 multiply by 0 squared. That will be equals to, now we are at 5, it will be 0.01 multiply by 9.8, but we are at 5 and we have now half of 0.01 and we want now to look for our V. So by so doing only, with the correct data and everything, then I am going to be in a position of getting this mark and getting that mark together with the correct formula. So the only thing that is left is for me to manipulate the equation, and when manipulating the equation, I find that my V now is equals to 9.89 meters per second. And remember, energy is a scalar quantity, so we are working with speed, so it means we don't necessarily need to indicate the direction on this one. So let's look at 5.5 quickly. Will the value of the cell phone's mechanical energy just before it hits the ground be greater, less than, or equals to? This one, the answer is straightforward. The answer should be equal to. The reason for that is, remember, mechanical energy is conserved. So if mechanical energy is conserved, regardless of where you are in the channel or the reference points you are considering. If mechanical energy is conserved, then it basically says the mechanical energy will be the same throughout. Because what do we say when we define the principle of conservation of mechanical energy? We say the total mechanical energy of an isolated system is conserved. So as long as the mechanical energy is conserved and the system is isolated, it basically says there will not be any change regardless of the reference point you are looking for. So key reason here, one will be mechanical energy is conserved. That is very, very key. Mechanical energy is conserved. That is now a key reason. But what is another supporting reason? The other supporting is the fact that we are told that ignore the effects of air resistance. Ignore the effects of air resistance. Then we say we are in a position of saying the system is isolated. Remember what we said about an isolated system is a system in which the net external force is equals to 0. So it basically says this will be now a supporting statement for us to ensure that when we give a reason, we explain that it will be the same because the mechanical energy is conserved and the system is now isolated. Any questions relating to this one?